Hey guys, this video is about Chateliers Principle. It's how an equilibrium reaction responds to a change after the equilibrium has already been established. If we change the concentration of something. All right, so right here, this reaction has already been at equilibrium, right? Here's H2, here's N2, and this one is for NH3. So the reaction is already sitting at equilibrium. And what has happened is we're going to add some H2. So we're going to add some of this to the reaction, and that's what this jump is. Okay, and so after that happens, H2 has to be consumed. So H2 has to go down. So that means the reaction is going away. Because if you think about it, if this is where K is, and we add some reactant to it, then that's going to affect Q, right? So Q is equal to the products over the reactants, and if this goes up, then that means Q goes down, and Q would no longer be equal to K. Q would then be less than K, and so the reaction would have to go forward because Q decreased, so it would be less than K. And remember, right here, Q is equal to K. All right. When the hydrogen initially goes up, it then has to be consumed, so it's going away from an increase. And if this is being consumed and the reaction is going forward, that means that NH3 is going to increase and N2 is going to decrease. Now H2 will be slightly higher than it was before the increase, but it's still going to be consumed, right? It'll be consumed in the reaction, okay? So it will be consumed. I will say it one more time, H2 will get consumed. All right, so if this increases over here, so the way that it likes to go away from an increase. So if this goes up, it's going to go away from it, the opposite direction. All right, so if we're going to look at these problems over here, with this example over here, it says arsenic can be extracted from its ores by first reacting the ore with O2 to form solid As4O6, which can then be reduced using carbon. So here's our reaction, and it says predict the direction of the shift of the following equilibrium position in response to each of the following changes and conditions. So if we add carbon monoxide, right, then this is going to go up. And so that would make Q bigger than K, and so the reaction is going to shift back. So it'll shift towards reactants. Okay, and then if we add or remove carbon, now this is not in K. Okay, so this is not in the K, the equilibrium expression. So therefore, it has no change. It's not going to affect the equilibrium. And then part C says if we remove As4, then the opposite is going to happen. Okay, so if we remove this, it has to make more of it because that's made Q too small, right? Because Q is first equal to K, it's at equilibrium. And remember, Q is equal to products over reactants. And if we lower the numerator, that makes Q smaller. And so therefore, then Q would be less than K, and so the reaction has to go towards the products. So it's going to make more product. So As4 will increase, CO will increase, carbon solid and As4O6 will be consumed in the reaction. But changing the amounts of these after equilibrium is established is not going to affect the equilibrium of the reaction. It won't change it. It'll still be at equilibrium. All right, Le Chatelier's principle, change in pressure or volume. So when we talk about gas reactions, a lot of the time we use KPs because pressure is easier for us to measure than molarity for gases a lot of the time. So two ways to think about this. If the pressure of the environment goes up, if pressure is going up, then that means volume is going down, right? Because of Boyle's law, they have an inverse relationship, right? If the pressure goes up, then it has to shift to the side that reduces the pressure. And so that's the side with less moles of gas. But I like to think about it as space instead of pressure. So anytime I see, okay, the pressure is going up, then I'll do this and I'll get this. So I have less space. So that means I'm going to move to the side with the least amount of gas. All right, so if this is the reaction over here, right here, if I'm giving it less space, then it's going to move to the side with the least amount of moles of gas. So this is the least amount, so it would move to the product side. And the other one, it says if the pressure in the environment goes down, so if pressure is going down, then that means volume is increasing, so there's more room. So it's going to move to the side with more moles of gas. So it would move to the reactant side because we have 4 moles of gas here total. All right, and then if there's equal moles of gas, then those changes wouldn't affect it at all. So there are 3 ways to change the pressure of reaction. One, we can add or remove gas, reactant, or product. That's what we just looked at. Okay, and so it shifts to the direction that undoes the change. So if it increases on one side, then it shifts to the opposite side to use it. And if it decreases on one side, it shifts towards it to use it. The second one is to add an inert gas. So an inert gas is something like argon or helium, right? They're noble gases. They're inert. They do not react. And what this will do is it will change the pressure of the system because we're putting more gas particles in there, but it's not changing the pressure of each one of these because they're all changing by the same amount. So all 3 of those would change, but they would change in the same amount, so the ratio of them wouldn't change, so it wouldn't affect Q, and therefore it doesn't affect the reaction. Okay, and then the last one is change in volume, and that's the way I like to think about these pressure changes. Even though the volume may or may not be changing, I still always convert it to that in my head so that I go to the right side. Okay, so the next question says, predict the shift in equilibrium position that will occur for each of the following processes when the volume is reduced. So if we reduce the volume for the first one, low volume, then it's going to shift to the side with the least moles of gas because the amount of space for the gases is getting smaller, so we're going to move to the side with the least moles of gas. So there's 6 moles of gas on the reactant side here. There's no moles of gas over here. So this one is going to shift to the products. All right, and then the next one, there are 2 moles of gas on the reactant side and 1 mole of gas on the product side, so it's going to shift towards the product where there's only 1 mole of gas because we're reducing the volume. We're making the volume go down. And then the last one, I've got 4 moles of gas on the reactant side and 4 moles of gas on the product side, and so there's no change because the moles of gas are equal on both sides. All right, and then the last thing we're going to talk about is change in temperature. If you've noticed, in all of the equilibrium problems, they always give you temperature, and that's because K will change if the temperature changes. So we have to consider that. So if delta H is negative, right, it's less than 0, then that means it's exothermic. It's a product of the reaction because it's being let off. So if energy or heat is added to this reaction system at equilibrium, the reaction will shift toward the reactant. And you can treat heat just like you would a reactant or a product. So if we're increasing heat, it's going to shift away from that increase back toward the reactants, and that's what we just said. Therefore, increasing the concentration of the reactants, because we're making more reactant because it's shifted towards the reactants, making K smaller. Because remember, your Ks are made by products over reactant. So if this gets bigger in the denominator, then K has to get smaller. Okay, if energy or heat is removed from a system at equilibrium, the reaction will shift toward the product. So we're still talking about exothermic reactions only. So if this goes away, if it goes down, then it has to replace that heat that's been removed, and it moves toward the product. This change will increase the concentration of the product, making K bigger. So just like in this example up here that I wrote down, if the products increase, and that makes K bigger, if you're removing the heat from an exothermic reaction. And then the opposite is true for endothermic reactions. So if it's positive, greater than 0, that means it's endothermic, and it can be written down on the reactant side. And so if energy or heat is added to this system at equilibrium, so we're going to add heat to this, and it's going to shift away from that increase. So it's going to shift toward the product, therefore increasing concentration of the product, making K bigger. If energy or heat is removed from the system, so this time we're going to remove it, and it's going to move towards that, so towards the reactants, because heat is a reactant when it's endothermic. This change will increase the concentration of the reactants, making K smaller. All right, so if you look at the picture, and I think I showed this in the very first video for equilibrium, that's how they do this. They change the temperature and the reaction shifts a particular direction. So as the temperature is heating up, the reaction is shifting this direction toward the reactant. And so if they wanted to make it more N2O4, they could make it cooler. In each of these examples, see how the changes as the temperature is increased. So here we have an endothermic reaction, right? It says it's endothermic because it's positive, it's not negative. So we have 181 plus N2 plus O2 goes to 2NO. And if we increase the temperature, so this is going to go up, the reaction will shift away from that. Products increase, and so therefore K increases. So K will get bigger. And then this next one is exothermic, so we're going to write it down as a reactant. And so we're going to increase this. So if this goes up, the reaction shifts away from that. It makes more reactant, and so K will get smaller. All right, and then how do the following changes affect the reaction? So we have this reaction written up here. And if we add N2O4, so this would go up. It would go away from that, and so it would move to the products. Addition of NO2, this would go up. It would move back toward reactant. Removal of N2O4, this would go down, so it would move toward the reactant to replace it. Removal of NO2, this would go down, so it would move toward that product to replace it. Addition of helium, no change, because helium is an inert gas. Decrease the container volume. Okay, so if we decrease the amount of space, then it moves to the side with the less moles of gas. So it would move this way because there's 1 mole of gas here and there's 2 moles of gas here, so this takes up less space. Increase the container volume. Well, it's going to move to the side with more moles of gas because there's more room. Increase the temperature. So this is an endothermic reaction. So if we increase the temperature, we're increasing heat. It's going to shift away from that, and it's going to shift that way, and so K would get bigger. If we decrease the heat, it's going to shift towards it, making more reactant, and so therefore K would get smaller. All right, what will happen to the number of moles of SO3 if the following changes are made while the reaction was at equilibrium? So we want to know what happens to SO3 this time. If O2 is added, the reaction will shift towards the reactant, and SO3 will increase. The volume of the container. Okay, so if the volume of the container is decreased, it's going to move the side with less moles of gas. And so that means it's going to move to the reactant, and so it's going to increase. In a rigid container, the pressure is increased by adding argon gas, no change, because argon is an inert gas. And so even though the pressure is affected, the pressure of all these is affected by the same amount, and therefore their ratio is not changing. The temperature is decreased. It says the reaction is endothermic. So my heat is over here. And if I decrease it, it's going to move towards it, and so SO3 will increase. Gaseous sulfur dioxide is removed. So if we remove this, it's going to move towards that decrease, and therefore SO3 would actually go down. What will happen to a reaction mixture at equilibrium if H2O gas is removed? So if this is removed, it's going to move towards that, and so the reaction shifts left. The temperature is increased, the reaction is endothermic. So we have heat over here, and if we increase the temperature, it's going to shift away from that. And so the reaction will shift right or toward product. Okay, an inert gas is added, nothing, no change. CO is removed. So if carbon monoxide is removed, then the reaction will shift towards that. And so shift toward product. And the volume of the container is tripled. So volume is increasing. So it moves aside with more moles of gas. And we've got 2 moles of gas here. We've got 1 and 1. So there's 2 moles of gas. And then we've got 4 moles of gas, so it's going to move to the right, shift toward product. Try to think of this stuff in terms of Q. It will help you on the AP test. Not all the answers do you have to think about it that way, but it really helps if you can get going quicker with that. So just think of the products over the reactants as Q. Don't worry about the coefficients and the exponents. So if your change is increasing reactant or increasing product, then you're just going to try to make it get back to K.